Hello and welcome, everybody. So, today I am covering everything there is to know about sinus, cosinus, tangents, and cotangents. Picture a stick, not a fancy stick, just a wooden stick shoved vertically into the dirt somewhere in the Egyptian desert, probably around 3,500 years ago. Some guy is standing next to it at noon, watching the shadow shrink. He does not know it yet, but he is doing trigonometry. He is also kicking off one of the longest intellectual journeys in the history of mathematics, one that ends thousands of years later inside the wave functions of quantum mechanics, inside every JPEG you have ever looked at, and inside the code running on whatever device you are watching this on right now. That is where we are going, all the way through, no shortcuts. So let us start at the beginning, because the beginning is a bit shocking if you have never thought about it this way. The Babylonians and Egyptians, going back to roughly 2,000 years before the Common Era, had figured out something practical. If two triangles have the same angles, the ratios of their sides are always the same, no matter how big or small those triangles are. You could have a tiny triangle and a massive triangle, completely different sizes, and as long as the angles match, the ratio of the vertical side to the horizontal side stays identical, always, without exception. This was not a theorem to them. It was not written up in a textbook. It was just a thing they noticed because it was useful. Surveyors needed to measure land that was hard to cross. Architects needed to plan slopes. Astronomers in Babylon were tracking the rising and setting of stars and planets, and those movements swept through arcs across the sky that demanded some way of talking about angles and distances together. The thing about a shadow is that it tells you something. If you know how tall the stick is and you measure the shadow length, you can figure out the angle of the sun above the horizon. And if you know the angle, you can predict the shadow. The relationship between a vertical object and the shadow it casts follows a precise rule, one that depends entirely on the angle of the incoming light. The Egyptians used this, the Babylonians used this. They did not have a name for the ratio, and they did not have a function in any modern sense, but they were using the idea sitting underneath what we now call the tangent. The Rhine mathematical papyrus, one of the oldest surviving mathematical documents we have, dating back to around 1,600 years before the Common Era, contains problems involving something called the secant. The secant was essentially the slope of a pyramid's face. How far does the outer surface lean for every cubit of height? That is a ratio of horizontal run to vertical rise. We will come back to that. Now jump forward a few centuries to ancient Greece, because that is where things get systematized. The Greeks were obsessed with circles, not just as shapes, but as the tool you use to think about everything from planetary orbits to the relationships between angles and lengths. The key insight they developed, which took centuries of collective work, was the chord. Imagine a circle. Pick any 2 points on that circle and connect them with a straight line. That line is a chord. If you know the angle at the center of the circle subtended by those 2 points, meaning the angle formed at the center with those 2 points on the rim, you can calculate the length of the chord. The chord length and the central angle have a fixed relationship. This was the Greek version of trigonometry. Not sines, not cosines, just chords. They thought in terms of chords because they thought in terms of circles, and circles were where all the geometric truth lived. The person who put all of this into a proper, tabulated, usable system was Hipparchus of Nicaea, working around 140 years before the Common Era. Hipparchus is often called the father of trigonometry, which is slightly ironic because the word trigonometry did not exist yet. He compiled what was reportedly 12 books of chord tables, essentially a massive lookup table for chord lengths at different angles, calculated for a circle of a specific radius. You would look up your angle, find the chord length, and use that to solve your astronomical problem. Those 12 books are lost. We do not have them. We know they existed because later writers described them, referenced them, built on them. What we do have is the Almagest, written by Claudius Ptolemy around 150 of the Common Era. Ptolemy's work includes an extensive chord table calculated with remarkable precision, good to several decimal places, and it is clear that Ptolemy was building directly on Hipparchus's approach. Ptolemy worked out what is now called Ptolemy's theorem. For any 4 points on a circle connected into a quadrilateral, the product of the diagonals equals the sum of the products of the opposite sides. This sounds like a geometry fact, but it is secretly a set of addition formulas for what we would now call sine and cosine. Ptolemy used it to compute his chord tables with stunning accuracy. He calculated the chord of half a degree, equivalent to the sine of a quarter degree, and got it right to 6 decimal places. He was doing all of this to understand the sky, to predict where planets would be, to understand eclipses. The practical pressure driving all of this mathematical development was astronomical. People needed to know where the moon would be next month. Navigators needed to understand the stars. Priests needed to know when certain celestial events would occur. Trigonometry at this stage was completely inseparable from astronomy. They were the same discipline. So this is the Greek picture. Chords, circles, 12 books of tables, all aimed at the sky. And then the story takes a hard left turn, because several centuries later, in the Indian subcontinent, something happens that will change trigonometry permanently. Indian mathematicians were doing their own astronomy, and they ran into the chord approach, but noticed a simplification hiding inside it. If you have a chord subtending some angle at the center of a circle, you can cut that chord in half and notice that the half chord is the sine of half the angle. The half chord is more convenient to work with than the full chord because it directly connects an angle to a ratio in a right-angled half triangle. So Indian astronomers started working with half chords directly, and this is where the sine function, as we would recognize it today, actually starts. The key text is the Aryabhatiya, written by Aryabhata around 500 of the Common Era. Aryabhata called the half chord Ja, which means bowstring. The shape of a bow and its string apparently reminded someone of an arc and its chord. He compiled tables of Ja values for every 3 3/4 degrees, from 0 to 90 degrees, calculated for a circle of radius 3,438 units. Why that number? Because it makes the circumference of the circle equal to 21,600, which is the number of arc minutes in a full circle of 360 degrees. The choice made the math work out neatly. Aryabhata also tabulated what he called koya, the ja of the complement angle. The complement of an angle is 90 degrees minus that angle. So the koya was the ja of the complementary angle, and this is the beginning of cosine, not in name yet, but in function. The tradition of Indian astronomical mathematics kept developing through the Gupta period and beyond. A later mathematician named Bhaskara I gave an approximation formula for sine that is surprisingly accurate without requiring the full table. The formula approximates sine of x as 16 times x times the quantity pi minus x, all divided by the quantity 5 pi squared minus 4 times x times the quantity pi minus x. That is a rational function, no sign in it anywhere, and it gives results accurate to within about 1% across the full range from 0 to pi. That is a remarkable engineering feat. And then the Kerala school, working in what is now the south of India, did something that should get much more attention than it does. Working around 1350 to 1400 of the Common Era, Madhava of Sangamagrama wrote down the infinite series for sine, cosine, and the inverse tangent. His followers developed these further and recorded the proofs in the Yuktibhasa, a text written in Malayalam that contains careful, rigorous derivations of the power series for sine and cosine, including the remainder terms needed to estimate the error when you stop the series partway. This is the calculus of trigonometric functions, arrived at roughly 2 centuries before the European development of calculus. The attribution of these series to Gregory, Maclaurin, and Leibniz reflects more about whose work got transmitted through European channels than about who actually did the mathematics first. This is increasingly being acknowledged in the historical literature, though the name Maclaurin series remains attached to the technique in most curricula. Now, the passage from India through the Arabic world and into Europe was not a single clean handoff. It was a slow, messy, centuries-long process of translation, reinterpretation, and rediscovery. But before we get to Europe, we need to talk about what the Arabic-speaking world did on top of what they inherited, because what they did was enormous. Muhammad ibn Musa al-Khwarizmi, the same person whose name gives us the word algorithm and whose book title gives us the word algebra, produced sine and cosine tables in the 9th century. He also gave an early table of tangents. Then, around 860 of the Common Era, a mathematician named Habash al-Hasib, which translates as the calculator, constructed the first table of cotangents. And al-Battani, working around 850 to 929 of the Common Era, was the first to construct what he called a table of shadows. This is where the tangent and cotangent arrive in their own right, through a completely different route than the sine and cosine, the gnomon, the shadow stick. Al-Battani studied the relationship between the height of a vertical stick and the length of the shadow it casts. If the sun is at angle theta above the horizon and your stick is height h, the shadow has length h divided by the tangent of theta. Equivalently, shadow divided by height gives you the cotangent of the angle. Al-Battani gave a complete table of these ratios for every degree from 1 to 90 degrees. Before anyone called them tangent or cotangent, the Arabs called them the shadow functions. Umbra recta meant the straight shadow, the horizontal shadow cast by a vertical gnomon, which gives the tangent. Umbra versa meant the turned shadow, the vertical shadow cast by a gnomon sticking horizontally out of a wall, which gives the cotangent. These shadow tables were used for timekeeping. The length of a gnomon's shadow tells you the time of day. Muslims needed to know exactly when to pray. Finding the direction of Mecca from any location on earth required spherical trigonometry involving all 6 trigonometric functions. So there was intense religious motivation pushing Arab mathematicians to develop these tools with extraordinary precision. Abul Wafa al-Buzjani, working around 940 to 998 of the Common Era, was the first mathematician to bring all 6 trigonometric functions together in a single unified treatment, establishing the relationships between them and computing them for a unit circle with radius 1. Setting the radius to 1 collapses a lot of unnecessary constants and makes the functions pure ratios, which is the modern convention. By around 1300 of the Common Era, Arab scholars had trigonometry as an independent discipline. The mathematician Nasir al-Din al-Tusi wrote what is considered the first standalone trigonometry textbook in history, treating it as its own subject rather than just a chapter inside an astronomy text. The word tangent itself took much longer to arrive than the function. The word comes from the Latin tangens, meaning touching. The geometric idea is this: draw a circle, draw a line that just grazes the edge of the circle at a single point, touching it without crossing through. That line is tangent to the circle. The length of that tangent line from the point of tangency to where it crosses another reference line turns out to be exactly what we now call the tangent of the relevant angle. Thomas Finke, a Danish mathematician and physician, used the term tangent for the first time in his book Geometria Rotundi in 1583. The function itself had been computed and used for at least 700 years before it got this name. The prefix co in cosine and cotangent was standardized by Edmund Günther, an English mathematician and instrument maker, in 1620. Günther used the term cosinus as an abbreviation for sinus complementi, the sine of the complement angle. If you have an angle theta, its complement is 90 degrees minus theta, and the cosine of theta is the sine of that complement. Günther did the same for cotangent, and in 1624 he introduced the abbreviation sin in print, along with tan. Samuel Jake introduced cos in 1696. Euler standardized the notation we still use today in his Introductio in Analysen Infinitorum in 1748. By the Renaissance, European mathematicians had access to a synthesis of Greek geometry, Indian half-chord functions, and Arabic trigonometric tables, and they started building on top of all of it. The most important European figure before the 17th century is probably Regiomontanus, born Johann Müller, but known by the Latin name derived from his hometown of Königsberg. Working in the 1460s, he wrote De Triangulis Omnimodis on all kinds of triangles, which is recognizably modern in its approach. Regiomontanus treated trigonometry as its own mathematical discipline and produced extensive sine tables accurate to many decimal places. Among those influenced by his work was Nicolaus Copernicus, who needed trigonometric calculations to work out his heliocentric model of the solar system. His student Georg Joachim Rheticus produced comprehensive tables of all 6 trigonometric functions for every 10 seconds of arc, an undertaking of staggering computational ambition. The European drive toward ever more precise trigonometric tables was driven, as always, by astronomical and navigational demand. Explorers crossing the Atlantic and Pacific needed to know exactly where they were. That required knowing the positions of stars with high precision, which required very accurate trig tables. So the names sine, cosine, tangent, and cotangent that you learned in school came from a chain of events spanning roughly 22 centuries. Indian astronomy, Arabic shadow tables, a medieval translation error, a Danish physician coining one word, an English instrument maker coining the co-prefix, and a Swiss mathematician standardizing the notation. That is the paper trail behind 4 names that get written on whiteboards every day all over the world. Now, let us talk about what these things actually are. Let us go back to basics and build upward carefully. Start with a right triangle. A right triangle has one angle of exactly 90 degrees and two other angles that must add up to 90 degrees between them. Pick one of those known right angles and call it theta. Label the sides. The side directly across from theta is the opposite side. The side next to theta that is not the hypotenuse. The hypotenuse, being the longest side always across from the right angle, is the adjacent side. The sine of theta is the length of the opposite side divided by the length of the hypotenuse. The cosine of theta is the length of the adjacent side divided by the length of the hypotenuse. The tangent of theta is the opposite divided by the adjacent, which is the same as sine divided by cosine. The cotangent is the adjacent divided by the opposite, the flip of the tangent, or equivalently, cosine divided by sine. Three other ones you might hear of. The secant is 1 divided by cosine. The cosecant is 1 divided by sine. And these plus cotangent form the full set of 6 trigonometric functions. We are mostly dealing with our 4 for now. Why are these ratios useful? Because they do not depend on the size of the triangle. If you have a right triangle where theta is 30 degrees, the sine of theta is always 1/2, no matter whether that triangle is a centimeter across or a kilometer across. The ratio is fixed by the angle alone. This means if you know an angle, you can figure out the relationship between all the sides. And if you know 2 sides, you can figure out the angle. In practice, this means you are standing a known distance from the base of a cliff. You measure the angle from your eye to the top of the cliff, and the tangent of that angle gives you the height divided by the distance. Multiply the distance by the tangent of the angle, and you have the height of the cliff. No climbing required. That is the shadow calculation from the Egyptian desert dressed up with names. But there is a problem lurking inside the right triangle picture. It only works for angles between 0 and 90 degrees. A right triangle cannot have 2 right angles. So if you want to talk about the sine of 120 degrees or the cosine of 270 degrees, the triangle picture breaks down. There is no triangle to point to. This is why the unit circle enters the picture. Take a circle with radius exactly 1, a unit circle, centered at the origin of a coordinate system with horizontal and vertical axes. Pick any point on that circle. The coordinates of that point are, by the convention we are now establishing, exactly cosine of theta and sine of theta, where theta is the angle measured counterclockwise from the positive horizontal axis to the line connecting the origin to that point. This is the modern, fully general way of thinking about sine and cosine. They are coordinates on the unit circle. The cosine is the x-coordinate and the sine is the y-coordinate. You can now talk about angles of any size, including negative angles going clockwise and angles bigger than 360 degrees, going around more than once. The functions become periodic. They repeat exactly every 360 degrees, or equivalently every 2 pi radians, because going all the way around the circle brings you back to where you started. This periodicity is not an accident. It is the mathematical core of what makes these functions useful for describing anything that cycles, tides, seasons, sound waves, alternating current, orbital mechanics. Whatever repeats these functions describe. There is also something worth sitting with about the relationship between sine and cosine specifically. They are the same function shifted horizontally. The cosine of theta equals the sine of theta plus 90 degrees. If you drew the sine wave and slid the whole thing 90 degrees to the left, you would get the cosine wave. They are identical in shape, amplitude, and period, just out of phase with each other by a quarter cycle. This phase relationship matters enormously in physics. When you have a sine wave and a cosine wave at the same frequency, you can add them in any combination and get another sine wave at that frequency, just with a different amplitude and phase. The set of all sinusoids at a given frequency under addition closes in on itself. Any combination of same frequency sines and cosines is still a same frequency sinusoid. This is why when you analyze signals at a particular frequency, you only need two numbers, a sine component and a cosine component, or equivalently an amplitude and a phase, to completely describe what is happening at that frequency. That is what the Fourier transform computes, and we will get there. Why radians? A radian is the angle subtended at the center of a circle by an arc whose length equals the radius. There are 2 pi radians in a full circle, because the circumference of a circle with radius 1 is 2 pi. Radians are the more natural unit for almost every advanced use of trig, because they make the calculus clean. In degrees, the derivative of sine is pi over 180 times cosine. In radians, the derivative of sine is just cosine. The pi fraction disappears, which is why all serious mathematics uses radians. On the unit circle, as theta goes from 0 to pi over 2 radians, 0 to 90 degrees, the sine starts at 0 and rises to 1, while the cosine starts at 1 and drops to 0. You can see from the geometry why, at 0 degrees, the point on the unit circle is at 1, 0, so cosine is 1 and sine is 0. At 90 degrees, the point is at 0, 1, so cosine is 0 and sine is 1. As theta passes 90 degrees and continues toward 180 degrees, the point moves into the upper left of the circle, so the x-coordinate, the cosine, goes negative, while the y-coordinate, the sine, stays positive. This is why the sine of 150 degrees is 1/2, same as the sine of 30 degrees. The point sits at the same height, just mirrored horizontally. As theta goes from 180 to 270 degrees, both coordinates are negative. sine and cosine are both negative. From 270 to 360 degrees, cosine is positive again, while sine is still negative. Then the whole pattern repeats. The tangent on the unit circle has a lovely geometric interpretation. At any angle theta, draw the line from the origin through that point on the circle and extend it until it hits the vertical line running through the rightmost point of the circle at x equals 1. The height at which that extended line intersects this tangent line, literally a line tangent to the circle at its rightmost point, gives you the value of tangent of theta. This is where the name tangent actually comes from geometrically. When theta approaches 90 degrees, that intersection point shoots off toward infinity. The extended line becomes nearly horizontal and never quite reaches the vertical tangent line at a finite height. This is why the tangent blows up to infinity at 90 degrees and at 270 degrees. The function has vertical asymptotes at those points. The cotangent is the dual version. It is the length from the origin to where the line extended from the point on the circle hits the horizontal tangent line at the top of the circle, the line tangent at the topmost point at y equals 1. The cotangent blows up at 0 and 180 degrees. For the same reason, the line from the origin going directly right or directly left never reaches the horizontal tangent line except at infinity. Now, for the deep geometric truth sitting underneath all of this. Take any angle theta, square the sine and square the cosine and add them together. You get one. Always. Sine squared plus cosine squared equals 1. Always. Why? Because of the Pythagorean theorem. On the unit circle, the point cosine theta, sine theta, is at distance 1 from the origin, because it is on a circle of radius 1. The distance from the origin to a point xy is the square root of x squared plus y squared. If that distance is 1, then x squared plus y squared equals 1. Since x is cosine theta and y is sine theta, we get cosine squared plus sine squared equals 1. Every trigonometric identity you have ever had to memorize flows from this one geometric fact combined with algebra. The double angle formulas, the half angle formulas, the product to sum formulas, all of them are downstream of this one constraint, plus the unit circle geometry. The Pythagorean theorem did not stop being relevant when you move from geometry to trigonometry. It went deeper. Rearranging the identity gives related ones. 1 minus sine squared equals cosine squared. 1 minus cosine squared equals sine squared. Divide through by cosine squared and you get tangent squared plus 1 equals secant squared. Divide through by sine squared and you get cotangent squared plus 1 equals cosecant squared. 4 identities, 1 geometric fact. From the same foundation, you can derive the addition formulas. The sine of the sum of two angles sine of A plus B equals sine A times cosine B plus cosine A times sine B. The cosine of A plus B equals cosine A times cosine B minus sine A times sine B. These formulas are not arbitrary coincidences. They fall directly from the geometry of rotating vectors in the unit circle, or from Ptolemy's theorem, or from multiplying complex exponentials. Several completely different derivations all give the same answer. The double angle formulas follow immediately. Sine of 2A equals 2 times sine A times cosine A. Cosine of 2A equals cosine squared A minus sine squared A. You can also write that last one as 2 cosine squared A minus 1, or as 1 minus 2 sine squared A, depending on which form is more useful. The product to sum formulas, which express products like sine A times cosine B as a sum of sines, were historically known as prostaphairesis formulas, from the Greek for addition and subtraction. Before logarithms were invented, multiplication of large numbers was extremely tedious. Astronomers who needed to multiply two 6-digit numbers would use these formulas to convert the product into a sum or difference, which is much easier to compute. In the 16th century, prostaphairesis was considered a serious computational technique. Napier's invention of logarithms around 1614 made it obsolete, but for a few decades, trigonometric identities were the state of the art in practical computing. That detail is easy to overlook but worth sitting with. The identities of trigonometry were labor-saving devices. The same set of formulas that students memorized to survive exams were once the software optimizations that enabled cutting-edge astronomical calculations. Now, calculus arrives in the 17th century, and with it comes a question that changes everything. What is the derivative of sine? What is the derivative of cosine? The derivative of sine is cosine. The derivative of cosine is negative sine. Take the sine function and differentiate it. Measure how fast it is changing at each point, and you get the cosine function. Differentiate cosine, and you get negative sine. Differentiate negative sine, and you get negative cosine. Differentiate that, and you get back to sine. The four functions chase each other in a cycle. Differentiate 4 times, and you are back where you started. This cyclical relationship under differentiation is the mathematical signature of oscillation. Anything that oscillates, anything that goes back and forth, anything periodic has this structure where repeated differentiation cycles through the same set of functions. Since the physical world is full of oscillating things, from pendulums to springs to electrons orbiting nuclei to electromagnetic fields, sine and cosine show up everywhere in physics. Not because physicists are particularly fond of them, but because oscillation is one of the most common behaviors in nature, and sine and cosine are what oscillation looks like mathematically. The derivative relationship also gives you the Taylor series expansions. If you want to express sine as a polynomial, an infinite one but still a polynomial, you can use the idea that the function can be approximated by summing up its derivatives at zero. The sine of x in radians equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, continuing with alternating signs and growing odd powers. The cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, alternating signs with growing even powers. These are exact equalities, not approximations. With infinitely many terms, they converge to the exact values of sine and cosine for every input. With just a few terms, they give extremely accurate estimates for angles near zero. This is likely how your calculator computes trigonometric functions, not with any geometric construction, but by evaluating a polynomial expansion, typically with algorithmic shortcuts to rearrange the computation into the most efficient form. The Cotg algorithm, used in many embedded processors, computes trig functions iteratively using only addition and bit shifting, exploiting pre-computed tables of the arctangents of successive powers of 2. The sine and cosine your phone's chip spits out when a GPS calculation demands them came from a chain of additions. The tangent's derivative is secant squared, and the cotangent's derivative is negative cosecant squared. These follow from the quotient rule applied to sine over cosine and cosine over sine, respectively. The antiderivative of tangent is the negative natural logarithm of the absolute value of cosine, which is a slightly surprising result. The logarithm showing up when you integrate a trigonometric function hints again at the deep connections between these families of functions. As noted earlier, the Kerala school had derived the power series for sine and cosine centuries before the European development of calculus. Madhava of Sangamagrama wrote down the series for sine, cosine, and inverse tangent around 1350 to 1400 of the Common Era. His followers developed these further and recorded the proofs in the Yuktibasa, a text containing careful, rigorous derivations, including the remainder terms needed to estimate the error when you stop the series partway. This is the calculus of trigonometric functions, arrived at roughly 2 centuries before Newton and Leibniz, worth repeating. Now we need to talk about Euler, because Euler did something that changed the game entirely. Leonhard Euler, the Swiss mathematician working in the 18th century, published his Introductio in Analysin Infinitorum in 1748. In this work, he established the modern analytic treatment of trigonometric functions, treating them as functions of a variable rather than as geometric line segments. He standardized the notation. He showed that sine and cosine are what you get when you look at the even and odd parts of the exponential function, and he derived the formula that Richard Feynman would later call the most remarkable formula in mathematics. Euler's formula says e to the power of I times x equals cosine x plus I times sine x. Let us sit with this for a second. E is Euler's number, approximately 2.718, the base of the natural logarithm, the number that shows up in compound interest, in population growth, in radioactive decay, in anything that grows or shrinks proportionally to itself. I is the imaginary unit, the square root of -1, and the claim is that e raised to an imaginary power produces cosine and sine. Why should this be true? The cleanest way to see it is through the power series. You know the series for e to the x. It is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Continuing. Now substitute I times x for x everywhere. You get powers of I cycling through. I to the 0 is 1, I to the first is I squared is -1, I cubed is -I to the fourth is back to 1, and so on in a cycle of length 4. When you collect the real terms, the ones without any I, you get exactly the cosine series. When you collect the imaginary terms, the ones multiplied by I, you get exactly the sine series. The two series for cosine and sine are hidden inside the exponential function interleaved. This is revealing something deep about the structure of mathematics. The exponential function and the trigonometric functions are the same thing, viewed through different windows. Exponential growth and oscillation are two faces of one mathematical object. When the exponent is real, you get growth or decay. When the exponent is imaginary, you get oscillation. When the exponent is complex, meaning it has both real and imaginary parts, you get oscillation that grows or decays, which describes things like damped pendulums and electrical circuits losing energy. The special case when x equals pi gives the identity e to the power I pi plus 1 equals 0. This puts together 5 of the most important constants in mathematics, e, I, pi, 1, and 0, in one equation. Whether this is beautiful is a matter of taste, but it is at minimum striking that such a concise relationship connects objects that seem to come from completely different parts of mathematics. What Euler's formula means geometrically is this: e to the power of I times theta traces out the unit circle in the complex plane as theta varies. When theta is 0, you are at the rightmost point of the unit circle. As theta increases, you walk counterclockwise around the circle. The real part of where you are is cosine theta. The imaginary part is sine theta. The complex exponential is a rotating hand sweeping around a clock face in the complex plane. This is now the way physicists and engineers think about oscillation. Instead of carrying around sine and cosine separately, they carry around a complex exponential and the real and imaginary parts take care of themselves. Wave functions in quantum mechanics are written this way. Alternating current in electrical engineering is analyzed this way. Signal processing uses this representation constantly, which brings us to Joseph Fourier, working in the early 19th century. Fourier was trying to solve the problem of how heat spreads through a material over time. He hit upon an idea that his contemporaries found outrageous. Any periodic function, meaning any function that repeats, can be written as a sum of sines and cosines at different frequencies and amplitudes. Take literally any repeating shape you can draw. A square wave, a sawtooth wave, something wildly jagged and irregular. Fourier's claim was that you can always express it as a sum of pure sine waves, each at a different frequency, each with its own amplitude and phase. This seemed completely wrong to people at the time. A sine wave is smooth and rounded. A square wave has sharp corners. How can you build sharp corners out of smooth curves? The answer is that you cannot, with finitely many terms. But with infinitely many sine waves at the right frequencies and amplitudes, the sum converges to the square wave. At the corners, the sum oscillates in a specific way, called the Gibbs phenomenon, a small overshoot that does not go away, but everywhere else, infinitely many sine waves reproduce the square wave exactly. This is the Fourier series. When you extend it to non-periodic functions, functions that do not necessarily repeat, you get the Fourier transform. The Fourier transform takes a signal and tells you which frequencies are present in it, how strong each frequency component is, and what its phase is. It decomposes a complex signal into its pure sine and cosine ingredients. Every time you listen to compressed audio, MP3, AAC, whatever format your streaming service uses, the compression works by taking the Fourier transform of chunks of audio, keeping the most important frequency components, and throwing away the quieter ones that your ear cannot easily distinguish. The music you are hearing has been decomposed into sine and cosine components, had the less significant ones discarded, and then been reconstructed. The sine and cosine are doing the compression. Every JPEG image you have ever seen works on the same principle. The image is divided into small blocks of pixels. Each block gets a version of the Fourier transform called the discrete cosine transform. The less significant frequency components are quantized or discarded, and the result is stored. When you view the image, the process runs in reverse. The discrete cosine transform, built entirely on cosine waves, is why your photos are small enough to send over the internet. Medical imaging goes further. MRI, magnetic resonance imaging, works by placing the body in a magnetic field, exciting hydrogen nuclei with radio waves, and measuring the radio waves they emit as they relax. The spatial pattern of those emissions is encoded in something called K-space, and converting K-space data into an actual image of the body uses the Fourier transform. The MRI machine is, underneath all the medical terminology, a Fourier analyzer. It decomposes the signals coming from your tissues into frequency components, uses the Fourier transform to figure out where those signals came from in space, and assembles that into the image your doctor looks at. Ultrasound images are built from sound waves bouncing off internal structures. The processing chain involves transforming time series sound data into frequency components, analyzing those components, and reconstructing a spatial picture, sine waves all the way down. Next, let us look at navigation, because this is where trigonometry touches nearly every person on Earth multiple times a day without them knowing. Your phone's GPS works by receiving signals from a constellation of satellites orbiting Earth. Each satellite broadcasts its position and the exact time its signal was transmitted. Your phone receives signals from multiple satellites and measures the slight time difference between when each signal was sent and when it arrived. Since the signals travel at the speed of light, that time difference gives you a distance to each satellite. Knowing your distance from 3 or 4 satellites in known positions, you are at the intersection of spheres centered on each satellite. Finding that intersection requires solving a system of equations saturated with trigonometry, specifically converting satellite positions from their orbital parameters, which involve angles and arc lengths, into three-dimensional Cartesian coordinates, and then converting your resulting position back into latitude and longitude. Every GPS fix your phone computes involves the sine and cosine of multiple different angles multiple times per second. GPS was the modern version of something navigators had been doing for centuries using the stars. To find your latitude at sea, you measure the angle of a known star above the horizon. Since you know the star's position in the sky at any given date and time, and you know the geometry of how the celestial sphere projects onto your visible horizon, you can compute your latitude from the sine and cosine of a few angles. The mathematics sitting beneath celestial navigation and the mathematics sitting beneath GPS navigation are, at the level of the functions involved, the same mathematics. The computations happen faster now. The principles have not changed. Computer graphics owes essentially everything to sine and cosine. When a 3D video game wants to draw a scene, it needs to take all the objects in the virtual world, described as collections of triangles in three-dimensional space, and project them onto your two-dimensional screen. This projection involves knowing where the camera is, what direction it is pointing, and how to translate between the camera's coordinate system and the world's coordinate system. All of that coordinate transformation is done using rotation matrices. Rotation matrices are built out of sines and cosines. A two-dimensional rotation matrix, the matrix that rotates a point around the origin by angle theta, has cosine theta in 2 of its entries and sine theta in the other 2, arranged so that multiplying the matrix by a point's coordinates produces the rotated point's coordinates. In 3 dimensions, rotating around any axis requires a 3x3 matrix whose entries are combinations of sine and cosine of the rotation angle every time a game character turns around. Every time the camera pans across a scene, Every time an animation rotates a joint in a character's skeleton, sine and cosine evaluated, multiplied together, summed thousands or millions of times per second. The GPU in your device is, among other things, an extremely fast machine for evaluating trigonometric functions and combining the results into transformation matrices. The lighting calculations in 3D graphics also depend on trigonometry. The brightness of a surface depends on the angle between the surface's normal direction and the direction the light is coming from. The Lambertian reflection model says brightness is proportional to the cosine of that angle, which is the dot product of the two direction vectors. Since the dot product of two unit vectors equals the cosine of the angle between them. Specular reflection, the shiny highlight on a smooth surface, involves the angle of reflection, computed using the angle of incidence, following geometric rules that are all trig. Architecture is another area where this shows up at every scale. The angles of roof pitches, the distribution of forces through arched structures, the resonant frequencies of large buildings under wind load. When engineers model how a tall building sways in the wind, they express the building's oscillation as a sum of sinusoidal modes, each at a different frequency. Fourier analysis applied to structural engineering. Now let us move into territory that gets stranger. In quantum mechanics, the wave function of a particle encodes everything knowable about that particle's physical state. For a free particle moving through space, one that is not subject to any forces, the wave function takes the form of a complex exponential, e to the power of I times kx minus omega times t, where k is the wave number, x is position, omega is angular frequency, and t is time. That complex exponential by Euler's formula equals cosine of kx minus omega t plus I times sine of kx minus omega t. The wave function of a free quantum particle is literally a combination of cosine and sine waves. The spatial frequency of those waves is proportional to the particle's momentum. Higher momentum means shorter wavelength, faster oscillation in space. The temporal frequency is proportional to the particle's energy. In the quantum mechanical picture of an electron trapped in a box, the allowed energy levels correspond to standing wave patterns inside the box. The wave functions at each energy level are sine waves. Sine of n pi x over L, where n is a positive integer and L is the length of the box. The allowed energies are proportional to n squared. The quantization of energy, one of the strangest features of quantum mechanics, comes directly from the constraint that only certain sine waves fit inside the box. The same way, only certain harmonics fit on a guitar string. The quantum mechanical behavior of electrons and the acoustics of a guitar string are both boundary value problems for the same wave equation, and both have solutions written in terms of sine. When you add many such sine waves together, many different wavelengths and amplitudes, you can construct a localized wave packet, a particle that is approximately in one place rather than spread out everywhere. This is the mathematical mechanism behind the uncertainty principle. A particle perfectly localized in space requires infinitely many different wavelengths added together, meaning infinite uncertainty in momentum. A particle with a precisely defined momentum has a perfectly sinusoidal wave function that extends infinitely through space, meaning complete uncertainty in position. Fourier's mathematics, written in the language of sine and cosine, is the reason the uncertainty principle has the form it does. The Schrödinger equation, the equation that governs how wave functions evolve in time, is a wave equation. Its solutions for systems with simple potentials are sine and cosine functions, or complex exponentials, or combinations of these. The entire modern understanding of how matter and light interact is written in the language of trigonometric functions. Now, let us talk about some of the deeper patterns that show up here. One of them is the question of why the universe seems to favor oscillation so much. Springs oscillate, pendulums oscillate, electromagnetic waves oscillate, quantum wave functions oscillate, sound oscillates, the tides oscillate, biological rhythms oscillate, heartbeats, circadian rhythms, neural oscillations, supply and demand oscillate in economic cycles. Population dynamics oscillate in predator-prey relationships. One answer is that oscillation is what happens when you have a restoring force, a tendency to be pulled back towards some equilibrium when you have moved away from it. Push a spring and it pushes back. Move a pendulum from vertical and gravity pulls it back. This happens everywhere because stable equilibria are everywhere. Things settle into stable states, and perturbations around those stable states produce oscillations. The mathematics of oscillation around a stable equilibrium to first approximation is always the same equation, the simple harmonic oscillator equation, and the solutions to that equation are always sine and cosine. So the reason sine and cosine appear everywhere is not that the universe has a specific fondness for triangles. It is that the universe is full of stable equilibria, and anything near a stable equilibrium oscillates, and all oscillation in its simplest form is sine and cosine. The triangle definition is a convenience for getting started. The circle definition is closer to what is actually going on. The differential equation is the deepest level. Sine and cosine are the two independent solutions to y double prime plus y equals 0, the equation that describes any system where the restoring force is proportional to the displacement. There is a related idea about the Fourier transform being a kind of universal detector for periodic structure. Anytime something repeats, the Fourier transform finds it. Economists use spectral analysis to look for cyclical patterns in financial time series. Neuroscientists use it to analyze brainwave data and find oscillatory rhythms. Climatologists use it to detect periodicities in temperature records. Astronomers use it to find the periods of variable stars or the orbital periods of exoplanets through periodic dimming signals. The question of whether there is a repeating pattern in this data is the question the Fourier transform answers, and it answers it using sine and cosine as its basis. There is also something worth sitting with about the connection Euler established between trigonometry and complex numbers. Before Euler, they were separate topics. After Euler, they were one topic. This unification has a philosophical dimension. It suggests that the separation we draw between growth and oscillation is somewhat artificial. Both are aspects of the same underlying mathematical object, the complex exponential viewed from different angles. When you restrict to real exponents, you see growth and decay. When you restrict to imaginary exponents, you see oscillation. The full picture requires both. This may be why quantum mechanics, which is the most accurate physical theory humans have ever developed, requires complex numbers. The wave function must be complex. Real-valued waves cannot encode all the interference patterns that quantum particles produce. Complex exponentials and the sine and cosine waves they contain are built into the structure of physical reality at its most basic level. Now, let us talk about the mathematics getting strange at the edges. Fourier's original claim was that any periodic function can be decomposed into sines and cosines. The mathematically precise version of this claim took a century to work out fully. The edge cases turned out to be strange. Not all periodic functions have Fourier series that converge pointwise everywhere. Mathematicians found functions whose Fourier series diverge at some points, or converge but to the wrong value. This led to an explosion of work on the foundations of mathematical analysis, the development of measure theory, Lebesgue integration, and eventually functional analysis. An entire branch of mathematics that grew out of trying to make Fourier's claim rigorous. One deep result in this area is that the set of functions whose Fourier series converges in the mean square forms a complete inner product space called an L2 space. The sine and cosine functions form what is called an orthonormal basis for this space. The word orthonormal means that any two distinct basis functions, when you multiply them together and integrate over a full period, give zero. They are perpendicular in a generalized sense. And each basis function integrated against itself gives 1. This is the abstract version of something you have probably felt intuitively. Different frequencies do not interfere with each other. Play two musical notes simultaneously, and the Fourier transform separates them cleanly because the sine waves at those two frequencies are orthogonal. They do not mix into each other's components. The fact that frequencies are orthogonal in this sense is what makes it possible to decompose signals into frequency components in the first place. The same structure shows up in quantum mechanics, where the allowed states of a quantum system form an orthonormal basis in a Hilbert space. and measuring the system projects the state onto one of the basis vectors in a way that is deeply analogous to computing Fourier coefficients. The mathematics of quantum measurement and the mathematics of Fourier decomposition are the same abstract structure: inner product spaces, orthonormal bases, projection. The sine and cosine functions are the concrete prototype for this entire family of ideas. There is also something philosophically interesting about the fact that while we can prove the existence of functions with strange Fourier behavior, functions so badly behaved that their Fourier series diverge, these functions cannot occur in physical situations. Physical systems have finite energy, satisfy regularity and conditions, and behave in ways that rule out the pathological cases. The full mathematical generality of Fourier analysis is richer and stranger than the physical world requires. The mathematics extends beyond physics, and we are left wondering whether that extension is meaningless generality or hints at something physical we have not found yet. That is not a solved question. Now, for the last part, prediction. Trigonometric functions have already been around for 2,500 years, and at every stage in that history, someone could have looked around and thought, this is probably as important as it is going to get. The Greeks had chord tables and thought they were doing pretty complete astronomy. The Indians had sine tables and thought they had the tools for pretty complete astronomy. The Arabs had all 6 functions and thought they had the tools for pretty complete science. Then Euler arrived and connected all of it to complex numbers and exponentials. Then Fourier arrived and made it a theory of all periodic behavior. Then quantum mechanics arrived and made it load-bearing infrastructure in the theory of matter. At each step, the functions that started as tools for measuring shadow lengths turned out to be something deeper, weirder, more connected to the universe than anyone had reason to expect. So what is the next step? One direction where trigonometric analysis is currently opening up is the study of data on non-Euclidean spaces. Classical Fourier analysis works perfectly on flat spaces, a line, a plane, a flat torus. But a lot of interesting data lives on curved spaces, the surface of a sphere, which is where geographic data lives, graphs and networks, which are how social data, protein interaction data, and internet traffic data are structured. These spaces do not have the clean Euclidean structure that lets you use Fourier transforms in the usual way. On the sphere, the analogues of sine and cosine are called spherical harmonics. They are more complicated functions, but they satisfy analogous orthogonality properties and can be used to decompose signals defined on spheres into frequency components in an entirely analogous way. Spherical harmonics show up in the analysis of the cosmic microwave background radiation, the afterglow of the Big Bang, mapped across the entire sky. The small variations in temperature across that sky map are decomposed into spherical harmonic components, and the pattern of those components carries information about the geometry and composition of the early universe. The generalization of this idea to arbitrary graphs and curved manifolds is called spectral graph theory and geometric deep learning. You take the eigenfunctions of the Laplacian, the natural generalization of the second derivative on the space, and those eigenfunctions play the role of sine and cosine in a generalized Fourier analysis on that space. This is a rapidly developing area of research with applications to machine learning on graph structure data, drug discovery where molecules are graphs, traffic prediction where road networks are graphs, recommendation systems where user-item interactions form graphs. Machine learning systems, specifically the transformer architectures behind modern large language models and image generation models, use something called positional encoding, which embeds the position of tokens in a sequence using sine and cosine waves at different frequencies. The specific frequencies are chosen to give each position a unique signature that the attention mechanism can use to understand where in a sequence each token sits. Sine and cosine are doing positional bookkeeping inside the AI systems, currently reshaping how software gets built. Quantum computing is another frontier. Quantum circuits are built from unitary transformations, which are generalizations of rotations. The fundamental building blocks of quantum computation, quantum gates, are parameterized by angles, and their action on quantum states involves sine and cosine, the same way rotation matrices do. Variational quantum algorithms, a leading approach to solving optimization and simulation problems on near-term quantum hardware, work by optimizing over parameters that appear inside sine and cosine functions in the quantum circuit. The landscape that these algorithms navigate is shaped by the trigonometric structure of quantum operations. Understanding that landscape when it has exploitable structure, when it becomes difficult to optimize, is an active research problem called the barren plateau problem. After the phenomenon where gradients of trigonometric functions vanish over most of the parameter space, making optimization slow, there are also open mathematical questions lurking in the neighborhood of these functions. The Riemann hypothesis, the most famous unsolved problem in mathematics, concerns the distribution of prime numbers, and its central objects are the Riemann zeta function and its zeros. The zeros of the zeta function, when plotted on the complex plane, encode oscillatory behavior that can be analyzed using Fourier-like methods. Some approaches to proving the Riemann hypothesis explicitly use spectral theory, the same general framework as Fourier analysis, applied to operators whose eigenvalues would need to correspond to the imaginary parts of zeta zeros. The sine and cosine functions sit in the background of one of the greatest unsolved problems in mathematics. What can we say about where trigonometry is going? Deeper into data analysis, as the scale and variety of data structures we need to analyze continues to grow. Deeper into quantum computing, as that field matures and requires better understanding of the trigonometric geometry of high-dimensional state spaces. Deeper into machine learning, as positional encoding and spectral methods on graphs continue to develop, possibly into a proof of the Riemann hypothesis if the spectral approach gains traction, and almost certainly into applications we cannot currently name, the way no one in Hipparchus's era could have named JPEG compression or MRI imaging as eventual applications of chord tables. The stick in the Egyptian desert cast a shadow. Someone measured the shadow. Someone noticed the ratio stayed constant when the angle stayed constant. Someone named the ratio. Someone found the ratio in a circle. Someone showed the circle was an exponential. Someone showed the exponential could decompose any signal. Someone showed the signal decomposition was the language of quantum mechanics. And now we are using the shadow stick ratio to train AI systems and build quantum computers. The functions are not done yet. They have never been done. Every time it looked like the story was complete, it turned out to be the start of a new chapter.